Okay, hope everybody's strapped in for this last edition of the Make Your Own Tube Preamp series with me, Dave from Fulton Street Amps. You already know I do this for the culture. I do this to get more people that are building tube gear that reflects their culture. What we're here to talk about is we're here to talk about the power supply of your tube preamp. So, in the last episode of the Build Your Own Tube Preamp series, we talked about the power transformer. So we know that the power transformer gives your tubes the high voltage and the low voltage that it needs in order for tubes to amplify. Okay, now there's an additional step we have to go through in order to make sure that our tube preamps are not noisy, so that the voltage that we get from the wall is not noisy. And there are a few steps that we have to take in order to do that. But before we go ahead and talk about that, we need to talk about one component that's really important in doing that. It's actually two components, but I've talked about one of the components before. One of them is a capacitor. The other one is called a diode. So we'll talk about how a diode works and how it helps our power supplies to filter our power that we get from the wall to be clean and not add any noise to your preamp. So I have the what we call the rectifier stage. So what the rectifier stage does is it converts our power that we get from the wall from AC. As you can see, it's an alternating current, which means it goes positive above the x-axis, and then we have some current that goes negative below the x-axis here. So it turns that current that goes positive and negative at almost 60 times per second. As you note here, I have 60 hertz, right? So one of the things we know is that we measure the pitch of a note. So the pitch of a note is do, re, mi, fa, sol, la, ti, do. Like if we think that was flat, of course, but if we think about the pitch of those notes that I went through in that scale, each note ascended in pitch. Each note had a frequency that was higher than the last. We measure frequency in hertz. So the power that comes out of the wall actually has a sound coming through it because it alternates from positive to negative at a frequency of 60 times per second. So that power that comes from the wall actually has a hum or noise on it that we want to filter out by turning into DC, which means our power will not alternate back and forth 60 times a second. We want it to alternate at 0 times a second. So we're trying to turn it from going positive to negative to just staying positive for our tubes. And I'm going to bring you through how that happens with a process called rectification, turning AC to DC. So how does that happen? Let's talk a bit about this component that we have here called a diode. Okay, so I'm gonna bring up our diode real quick. Okay, so what a diode does, a diode has two parts. One part is called the anode and one part is called the cathode. So what a diode does is a diode will actually depend on how you have it oriented. If you pass your guitar signal through the anode, then the cathode, if you look at a diode, it's going to have a white stripe on it or some sort of stripe. So the stripe is going to be the cathode and the non-striped end is going to be the anode. If you pass it through when it touches the anode side or the side that doesn't have a band first, what it's going to do is chop off all of the negative part of your guitar signal and just leave you with the positive voltage. Okay, if you flip it around and you have your guitar signal go through the banded end or the cathode first, what it's going to do is chop off all of the positive part of your guitar signal and just leave you with the negative part. So not only does it just chop off the positive or negative part of your signal, is also going to cut down the volume of your signal by about 0.7 volts. Okay, so it's going to chop off either the positive or the negative end of the signal depending on which way you have the diode flipped around, and it's also going to cut your volume some. And we use the diode in order to go from positive, a signal that goes from positive to negative to just staying positive, and that's called rectification. So I'm going to show you in our schematic how we do that, how we accomplish that. Okay, so let me open up that other schematic I had before. Okay, okay, so here we have our voltage coming in through the wall. Okay, we have it going through a power transformer. Now, one thing to note is that if you have a power transformer that has 3 wires on the side, one of those wires is something called the center tap. Now, when you run a signal through a center tap transformer, something special happens. You get the original version of the signal that may be boosted in voltage. In this case, it's boosted. It boosts the voltage by double. So we end up with 240 volts on this side rather than 120 volts. We get the original signal, and on the other side of it, we get the signal shifted forward a little bit. So what that is called is it's called a phase shift. So it is a version of your signal that is delayed by a very tiny amount. So it's delayed just enough where if you added these signals together, you see that they would cancel out. As you can see, we have like a peak here and we have a valley here. So if we added those two together, it cancel out. Same thing here. We have a valley here and we have a peak here, and they would cancel out. So we actually use that bit of a phase shift or time delay in order to help us get all of our signal to be positive rather than negative. So what happens is this signal that has both positive and negative, as you can see, is passing through the anode first and not the cathode. So going back to when we had our picture of our diode, whenever we go and put a signal through the anode first, it's going to leave us through with the positive part of our signal left. So let's go ahead and go back to our schematic and let's take a look at what's happening. So we send this signal through the diode and it leaves us with the positive part of that voltage coming through the wall. Okay, so note that the voltage coming from the wall repeated at a cycle of 60 times per second, right? So what we noticed here is that when we fed this voltage through our power transformer, again, we see that it has this tap in the middle that we ground. And what that does is it delays our signal, phase shifts our signal. So what happens is we do feed our signal through the anode of this diode first, which means we're left with the positive parts. But as you can see, since it shifted the signal forward, what we have is we actually have the positive parts of our signal that actually fill in the gaps that this signal left when it was rectified. So when we bring those two signals together, we have all of those negative peaks that have turned positive now. And now, rather than having a signal that repeats at 60 cycles per second, we have a signal that repeats at 120 cycles per second. So if you double the frequency of a sound, you actually get the sound at its octave. Okay, so 120 hertz is still a hum. It's just a hum at a higher frequency. Now, as you can see, the diode helped us to get all of our voltage positive, but what we have to do is we have to smooth that out now. And what we're going to do is we're going to use a combination of capacitors and resistors to smooth that out. Now, how exactly does the capacitor do that for us? Well, what a capacitor does, I've alluded to this before, but a part of the function of a capacitor is to store energy. So here I have a capacitor. It's rated at 450 volts, and it will store 16 microfarads of charge. So that's a measure of how much energy it has stored in it, and it will charge up to 450 volts. Now, what a capacitor is going to do is if we're running a signal past our capacitor, if it noticed that the voltage of the signal that's coming past that capacitor is falling, What that capacitor is going to do is it's going to discharge some of that positive voltage to add to the signal that has this falling voltage. So it's going to help to resist against that voltage falling. Okay. But the thing is, there is no capacitor that is large enough in the world where you just hook that capacitor up to the signal that's been rectified by diodes to make it completely smooth. So you're going to end up with a signal that looks like the one that I'm drawing right here. So it's still going to have some humps. You're still going to see the fact that it's been rectified by diodes. So you're still going to have some hum that's present there. It's just going to be a little bit less annoying. Okay. So it's just going to smooth out this hum slightly, and you'll still have these humps that are on the top of your signal. Now, if we remember back to our last section, we've noted that when you combine a capacitor along with a resistor, what ends up happening is we get a filter that is going to cut down the volume of signals that are at a certain frequency. And what I'm going to do is I'm going to put some of these values into that filter calculator that we took a look at before. Okay, so I'm just going to put in here, I'm going to put RC passive filter calculator. Okay, so it's going to check to make sure that I'm a human. Okay, now remember I said that the pattern or the sound of this noise that we have now is at 120 hertz. So we are looking to take anything that is 120 hertz or below that, and we want to cut down the volume of that signal. So here we have a 22K resistor, 22,000 ohms. And we said we have a 16 microfarad capacitor. What it's going to do is it's going to take any signal that has frequency content that is bigger than 0.45 hertz, and it's going to cut down the volume of that signal by 30%. Okay, so not cut it down by 100%, we said by 30%. Okay, so each time we go through one of these resistor and capacitor filters that we have, so this is called when we have a resistor and a capacitor to ground, this is a low pass filter. So it's going to leave anything lower than 0.5 hertz alone. But our noise is at 120 hertz. So it's going to be chopped down by this filter. So if we come over here, every time we pass through a resistor and a capacitor, it is going to cut that noise down. Okay, until we get to the point when our voltage actually looks just like this, where we have a flat line that goes across. Okay, so that is exactly how we put together capacitors, resistors, and diodes in order to create. So this is our high voltage path. So we have about 240 volts here. By the time we get down here, with the way that this power supply is set up, we're going to end up with about 247 volts at point C. Okay. Now you might start to think about, well, how exactly did you come up with this combination of resistors and capacitors? So if you think about it right now, we are looking at the preamp for a 5E3 Deluxe model from Fender, which has a well-established schematic. And if you look up some of these schematics, they will tell you exactly what voltage they're going to be feeding to their tubes. So what I did was I looked up so the 5E3 schematic. There is a site by a gentleman named by the name of Rob Robinette, who is amazing when it comes to learning about tube gear and building your own gear. He steps you through the process step by step, and his site robrobinette.com is a wealth of information. So this node that we have coming off of our last filter cap, so it's our cleanest stage that we have in our power supply. So if we take a look, as we move from the diodes through successive stages of those resistors and capacitor, our power gets cleaner, right? We get less of that ripple. So we want to hand the most sensitive stage where our guitar signal is the weakest, we want to hand that the cleanest power that we can. So in this particular amp, it's handing its preamp a voltage of 250 volts, okay? And you see where I got those values for the filter capacitors here, okay? Now, you'll start to ask, hey, how did you get the values for those resistors? I'm going to get to that in just a second, okay? So, I was shooting for getting around 250 volts fed to my tubes. I also, with the tube that we're using in the 5E3, I wanted to use a 12AX7 or an ECC83 tube. It's commonly available. It's really easy to find a 12AX7, and they use, for the majority of guitar amps that are out there, they use 12AX7s or ECCs 83s, so they're pretty easy to find. Okay, now in terms of figuring out, like, okay, what are these resistors, right? What are these values that we want to have? The thing to note is that whenever a signal passes through a resistor, you're going to have a voltage drop. Okay, so one of the ways that you can actually ballpark how much your voltage is going to drop, and also know like what type of power transformer I need to get, is you have to know what tubes you're using, and the tubes that you're using are going to let you know exactly what voltage they like to be fed with and how much current they're going to use. And the amount of current that these tubes are going to demand are going to guide you towards picking the right transformer. So I was looking for a transformer that had about 240 volts once you fed it with 120 volts. Okay, so now how exactly did I come up with that number? Well, there are a few ways to go about doing that. Okay, so one of the things that you can do is you could look up a tool called the Duncan Amps power supply calculator. So you can tell it what type of power transformer you have. You can tell it how you're rectifying the power, okay, and it will actually let you know how much voltage you'll end up with in your preamp. And I use this software in order to figure out what values I wanted to put for my resistors in order to get it down to that voltage of 250 volts that I wanted to feed my preamp tubes. Okay, so that is one thing to look at that you can use to figure out your resistor values, and I'll come back around to that and show you how I used it. Okay, now I had already said I wanted a power transformer that could give me 240 volts on the secondary. So this is the primary of the power transformer, this is the secondary, along with giving me another secondary winding that could provide 6 volts for my low voltage winding. Now, how do I know that my tube needs 6 volts in order to run for its for its filament? If you look up a tube data sheet, it will tell you. Okay, so all you have to know is the name of your tube, so we can look it up together. So we'll put in ECC83 data sheet. Okay, so if we put in ECC83 data sheet, it will actually tell us. So it says that it's going to need So UF stands for filament voltage. So it needs 6.3 volts on the filament. Okay. So what it also tells us is it also tells us how much juice is going to try to consume from your power transformer as well. So it tells me that it's going to try to consume 150 milliamps of current. Okay, so we're gonna try to write those things down. Okay, so I'm gonna pull up a little spreadsheet and we'll try to get those things written down. All right, so we're gonna say I had another tube setup in mind that I was doing some calculations for, but we're going to get rid of this. So we know on our low voltage winding for the 6.3 volt winding, we looking at the data sheet, it said that we're going to need 300 milliamps, right, of current. Okay, so 300 milliamps is equal to 0.3 amps of current. Okay, so that's for the low voltage. Now, how about the high voltage? So it's also going to tell you, hey, what kind of voltage do we need and how much current are we going to be asking from our power transformer? That's also going to be in your data sheet. Okay, so it's telling you that it's typically going to pull about 1.2 milliamps from the plate. So A stands for anode, or which is another word for the plate. Okay, so I'm going to put that our high voltage winding is going to need 1.2 milliamps. Okay, so now I'm going to get rid of this formula real quick. Okay, so we need, for our high voltage, we need 1.2 milliamps. Okay, and for our low voltage, we're going to need at least 0.3 amps on the low voltage. Okay, so when I go to look for transformers, I'm going to look for transformers that get, I can put in 120 volts, and I can also get, so input, and I could get 240 volts on the output, and I also want 6.3 volts on the output. So one thing to note is that with transformers, we typically don't talk about input or output. We'll talk about the primary winding, and we talk about the secondary winding. So on our secondary, I want 240 volts. And I also want a 6.3 volt secondary. Okay. Now, there is a nice transformer that Hammond happens to sell. There is a site that I go to for a lot of my supplies, and it's called Amplified Parts. So they call these particular transformers that Hammond makes, they call them bias transformers. So okay, so we're going to pull this up, and what it's going to ask you for is it's going to ask you what voltage do you need on your secondaries and how much current do you need it to be able to handle. Well, if we take a look at our data sheet, it tells us that for our low voltage winding, or the filament winding, we need 300 milliamps, which is 0.3 amps. So if we look at our transformer, all of these transformers will be able to provide more than 0.3 amps. Okay, all of them will. And in terms of our high voltage winding, we said that we would like to have at least 240 volts on the secondary. So these three on the top provide that for us. And looking at our data sheet, what we wrote down is that our plate, or the anode, is going to demand 1.2 milliamps of current. Now, if we take a look at our transformer, we can see all of these transformers provide at least 1.2 milliamps of current, okay? Now, paying attention to these current ratings are important, as we noted before that what current is it's a bunch of electrons running through a wire, and the wire provides friction on those electrons. Much like any type of friction, when you rub your hands together, your hands get warmer. Same thing with electrons running through a wire. Electrons running through a wire creates heat, and these transformers are nothing but wire that's wrapped around a magnet, and that wire has insulation on it. Once the transformer gets too hot, the insulation melts and wires touch each other inside the transformer that aren't supposed to, and your transformer fails. Okay, so it looks like a really good fit for us. The lower the current handling capacity of a transformer is, typically the more affordable is going to be. So I would pick this one. It's going to give us our low voltage for our tube and our high voltage, and it has enough current capacity for us. So I would pick this one, which would be the 2C1C6. So this one would cost $50. They have one with even more current capacity that's going to be less expensive, the E6. P261E6, which is going to cost us $46.25. Okay, so we note that our power transformer is going to put out 250 volts. Okay, so I have that power supply designer here loaded up, and what I'm going to show you is that I've given it a power transformer that's going to put out 250 volts. Okay, and I've chosen the type of rectification that we have here is called full wave rectification. So it requires you to have that center tap on the transformer, and we saw why. We needed that signal to be shifting in phase a little bit so it can fill in the gaps of that signal that wasn't shifting in phase, right? Okay, so you can come in here and you can choose what type of rectification we have here. So here I have solid state rectification, which means we're using diodes rather than a tube, and I'm using full wave rectification, which is what we have here, and it's putting out 250 volts. Now notice that number that we had here, so 2.4 milliamps. If we take a look at our data sheet for our tube, so I'm actually going to pull up another data sheet just so we can get familiar looking at different types of data sheets. What it says is that this tube is a dual triode. So there are two 12, there inside of one 12AX7, you actually have two tubes that you can use for amplification. Okay, so each of those sections are going to use 1.2 milliamps of current. Okay, so in total we're going to use 2.4 milliamps of current on our high voltage winding. And remember, we said we're shooting for about 250 volts to be supplied to it. Okay, so in my power supply calculator, what I told it was, hey, I have these filter caps. Each of them are 16 microfarads like we had in that diagram. Okay, and what my tube is going to pull, my tube is going to demand 2.4 milliamps. Okay, that's here. Now, this point, the voltage here is called VI1. So if we take a look at VI1, we see we're right on target. We have 248 volts and we're getting what we want. Let's say you wanted to shoot for less voltage on your power tubes. One of the things to note is that the lower voltage you have applied to, not your power tubes, your preamp tubes, the longer it lasts, okay? But it's a balance. They'll last longer, but you'll also get less gain out of a stage. Let's say you wanted less voltage. We know the higher a resistor is, the more voltage is going to drop, okay? So let's say I wanted to make this resistor 22 kilo ohms. What would that make my voltage? you see it drop my voltage from 250 to 209 by changing that resistor. So you can play with this power supply calculator in order to figure out what your values are going to be for your resistors, and figure out like how to tweak those values to get the voltages that you want in your power supply. So I'm going to change this back. I think I had this to 10K to get the voltages I want. Okay, so that's what we have. So the other thing, we've actually talked about the power supply. Now some folks will want to take their preamp and plug it into a mixing desk using an XLR cable, because we know that XLR cables cut down on noise, right? When we run long lengths of XLR cable, that is not going to cut down on the high end of our signal or anything like that. Now, there are a couple of considerations that we have to take into account when we do that, okay? And we will talk about those considerations next on part B of this series on finishing out your tube preamp.